How does a computer work? The mystery revealed. Basic building blocks of a computer and logic gates. We use computers daily, but we don't know how computers are built and how they work logically. We feel a deep sense of responsibility to share our simple but exciting content about building blocks of a computer and its logic. Have you ever wondered how computers think? Can a computer think at all? Can a computer understand anything? Well, let me tell you this. Computers can't think, they can't understand anything. Computers just do what you tell them to do in a certain way, programming. The day they start thinking, they'll no longer be called computers. So a computer doesn't know anything, just like a bicycle doesn't know it is being moved. Okay, if a computer doesn't know anything, then what's really happening inside this magical machine that changed the whole world? After all, how can a machine do everything we say without knowing anything? Isn't it mysterious? So let's reveal this mystery with a simple question that we all know answer for. How we really think and interpret a language. We know the letters, words, numbers and their meanings intuitively because we've been using them since our childhood. We just simply interpret a language with some logic. Let me explain this with a long sentence. Albert Einstein admired Indians for their invention of zero and for their decimal number system, which we all use today. The key words our brain uses to understand this long sentence are for, and which. With some logic, which is grammar in this case, we intuitively come to know the following four sentences from the long example sentence. Albert Einstein admired Indians. Indians invented zero. Indians invented decimal number system, and decimal number system is used all over the world today. We know this intuitively. Isn't it magical? Yes, our brain does this magic to process conversations. But what about computers? Computers don't know the letters, words, numbers and the meanings as we do, right? Then what's really happening inside this little mysterious box that sent people to the moon, changed the way we communicate, and without which we can't spend a single day? Let me explain this way. Computer is an electronic machine, so it can understand just on and off. Okay, but how the logic was implemented in a computer, and how the computer executes our instructions with just on and off. It's crazy, right? Yes, but let's remember this legendary mathematician first. The son of a shoemaker from England played a vital role in converting logic into mathematical form with his passion and love for mathematics, logic and philosophy of mathematics, George Boole. He was born on 2nd November 1815 in England. He is best known for his books, The Mathematical Analysis of Logic 1847 and The Laws of Thought 1854, which contains Boolean algebra. Regular algebra works on numbers, and its basic operations are addition, subtraction, multiplication, and division. But Boolean algebra works on Boolean variables true and false. The basic Boolean operations are and, or, and not. Boolean logic is the foundation of the information age. Unfortunately, George Boole died on 8th December 1864 in Ireland at the age of 49, walking a distance of 3 miles in a heavy rain from his home to the university for the dedication and love for teaching, and lectured wearing his wet clothes. Boolean algebra works on sets, and it is the foundation of computer circuits that are made all over the world today. Boolean algebra is used to reduce the number of components in a circuit, thereby lowering the cost and complexity of the circuit. Okay, but what are the basic components of a computer circuit, and how can they work with just on and off? Before getting into that, we must know about a key element of every electrical circuit, a switch. A normal switch controls the flow of current in a circuit by opening and closing the circuit mechanically. All the magic in a computer is done by these magicians called automatic switches. Relays were used as automatic switches in early days of computers. Then vacuum tubes replaced relays. Now transistors are being used in computers. Tomorrow we may have some other technology to build computers, and they can be optical computers with photons and not electrons, or quantum computers that can represent both on and off at the same time, and they can be thousands of times faster than our regular computers. A huge research is going on these topics, and you can do it too. For simplicity, let's pay attention on just relays. We can explore about vacuum tubes and transistors in later episodes. There are many types of relays available today for many different applications. But let's see how a basic relay works. A basic relay is an electrically operated electromechanical switch. In a relay, we'll have two independent circuits, the control circuit and the load circuit. The key components here are the coil, which is an electromagnet in the control circuit, and the movable mechanical component armature with a spring in the load circuit. The coil acts like a magnet when current flows through the coil, and that pulls the armature of the load circuit, which causes the circuit to be closed and the current flows through the load circuit. When there is no current in the coil, there will be no magnetism, and the armature is pulled back mechanically with the spring and the circuit opens, so there will be no current in the load circuit. So the current in the control circuit is able to control the current in the load circuit automatically. Congratulations, we've made it. Till now, we've seen the normally open relay, where load circuit is open by default when there is no control current, and the load circuit will be closed when there is control current. And there is another type of relay which is normally closed, which works exactly opposite to the normally open relay, where load circuit is closed by default when there is no control current, and the load circuit opens when there is control current. But there is one problem here. We can directly use a switch in the load circuit, right? Why are we controlling the load circuit using a control circuit? Definitely not for fun. And yes, there comes the topic of amplification, converting a low signal into a high signal. Relays are normally used to control a high power circuit with a separate low power circuit. Relays were first used as amplifiers in the long distance telegraph circuits to amplify the low incoming signal. But before getting into the amplification, we need to know the basics of electronics. Voltage, current and resistance are the basic concepts in electricity, V, I and R. We can compare electricity with a flow of water in a pipe. We can assume voltage as the water pressure, current as the amount of water flowing, and the resistance as the width of the pipe. As we know, the wider the pipe, the more the water will flow. In the same fashion, a wider wire leads to a low resistance and a high current. Voltage and current are directly proportional to each other at constant temperature. So a high voltage leads to a high current in the circuit when the temperature is assumed constant. V equals to IR, the famous Ohm's law, named after a German physicist George Siemens Ohm. Current and resistance are inversely proportional to each other. A high resistance leads to a low current in the circuit. We want you to pay attention to the length of the wire and its implications on resistance and current in the wire. The length of the pipe can't affect the width of the pipe, and also the amount of water flows through the pipe. But in a circuit, a lengthy wire leads to a high resistance and a low current in the circuit. So over the long distances, the resistance increases because of the lengthy wire. But electrical equipment needs a certain amount of current to run, not lower and not higher. So we use relays to amplify a low current to a high current. Let's see a relay working as an amplifier. Even if we give a low voltage to the control circuit and a high voltage to the load circuit, the low current in the control circuit is able to control the high current in the load circuit. The input of the relay is low and the output of the relay is high, which is nothing but the amplification. And it's just that simple. Relays, vacuum tubes and transistors all are invented to amplify the current, but all of them can be used in creation of logic gates, and those logic gates are the basic building blocks of a computer. Relays were used extensively to perform logical operations in early computers. The first programmable relay computer was built in 1938 by Konrad Zuse, a civil engineering student from Berlin. Dramatically, relays were replaced in computers with vacuum tubes by 1945. Because relays are electromechanical, huge in size, very slow to switch, takes much power and gives more noise. Okay, but how can a relay, which was invented for amplification, be used in creation of logic gates of a computer? Yes, that's a great question. Here in computers, we use relays both as automatic switches and sometimes as amplifiers. There won't be a huge difference between control voltage and load voltage in a computer relay. We now know relays, vacuum tubes and transistors are used in creation of logic gates. But what is a logic gate? Before a logic gate, let's see what a simple gate is. A gate can allow or block people based on whether it is open or closed. In the same way, a logic gate can allow or block output current based on whether input currents are high or low. And these are called logic gates because they allow output based on a logic applied on the inputs. Note that number of inputs can be one or more, but number of outputs can only be one. In computer terminology, High current or high voltage, which is on, is called as 1 or true, and low current or low voltage, which is off, is called as 0 or false. We have three basic logic gates, and they are AND, OR, and NOT. AND gate, it allows output current be high only when all the input currents are high. Output of one gate is low if at least one input is low. Let's see the simple 2-input AND gate. When we connect two relays in series as shown, then it behaves as AND gate and allows output current be high only when both the inputs are high, otherwise it outputs low. OR gate. It allows output current be high if at least one of the input currents are high. It makes output current be low when all the input currents are low. When we connect two relays in parallel as shown, then it behaves as OR gate and allows output current be high if at least one input is high. Otherwise it outputs low. NOT gate. It just flips the input and gives the output. It makes output current high when the input current is low and makes output current low when the input current is high. NOT gate is just a normally closed relay and its output is just the negation of input. NAND, NOR, and buffer gates are the exact opposite gates of AND, OR, and NOT gates. NAND gate is nothing but the OR circuit with normally closed relays. NOR gate is the AND circuit with normally closed relays. Buffer gate is nothing but a simple normally open relay, and it outputs the same as the input, which is mainly used in propagation delays. Buffer or NOT gates are the only gates that can have only one input. Here are the logic tables of NAND, NOR, and buffer gates. Let's recap everything we learned in this lesson. Computers can't think, and they don't know what they are working on. They just use on and off to do the stuff. We can tell a computer to do something logically through a programming language. George Boole invented Boolean algebra, and it works on Boolean variables true and false, or 1 and 0. The basic Boolean operations are AND, OR, and NOT. Relay is both an automatic switch and an amplifier. Finally, we've constructed AND, OR, and NOT gates and also their counterparts, NAND, NOR, and buffer gates with relays, and seen how they work logically. And now we know how computers are built and how they work logically at a very basic level. We hope you liked this video. Let's meet again with our next video. How does a computer perform addition, subtraction, multiplication, and division? Thank you.